Welcome back again. Thank you very much for leaving the lovely view and coming, I hope, to have a lovely view of Dick's talk. Dick Feely from NOAA Pacific Marine Environmental Laboratory, one of the grand old men of ocean acidification. Certainly grand. Dick's been working in this area for many years and contributing quite amazingly in two separate, though clearly related spheres. Number one, actually doing measurements that show what's going on in the world, and two, trying to persuade other people to do the measurements as well. And so here he'll give a brief presentation.
Andrew, I just wanted to point out that several of us in the room were laughing at Dick when he was doing this in 1984.
No doubt. And undoubtedly there'll be people in the room laughing yet. But Dick got a Heinz Award for this work, very well deserved, and numerous others awards. So he's going to tell us a little bit about Global Ocean Acidification Observing Network, because that's one of the larger plans to look and see what really is happening all around the world in this rather important area. What we're going to hone him in on in the discussion afterwards is, and how does a regional view, such as CCAN might provide, fit together with that? Thank you, Dick.
Before I start, I want to take this opportunity to personally thank Andrew for his outstanding leadership, for helping make CCAN what it is today. This has been a very exciting effort, and I want you all to know that CCAN is leading the world in what we're trying to do here, and I think it's your efforts that have made a difference. When we go to look at what's going on at the international level, it's important to realize that these are networks of networks, and you start with the best networks you have, and you integrate that into other networks. So there isn't a grand observing system in the sense of a major pot of money. It's individual networks that work together to provide the global ocean network. That's the way it works. So that's the key message here. So with that then, why we take a global approach is because we have to. We have no choice to do. With the global observing system and the global nature of ocean acidification, we have to begin to work together to develop the coordination strategies and goals to integrate what we have at the CCAN level all the way up to the international level. That's what we've been working on. This slide is just a composite slide to show you the many different kinds of biological systems that will be impacted globally, from coral reefs to cold water corals to mollusks, and the interactions that we have between the very basic processes that we're just beginning to understand with the single species and how they interact as an ecosystem. We're just beginning to get started with this, and this is why it's kind of very critical to work at the large scale, because each one of these ecosystems will behave differently, and we have to understand how they behave. And so if we don't develop a network with the consistent set of best practices, we would never be able to get where we want to go. This is one of my favorite slides. It shows the scientists' best estimate of where our understanding right now has vulnerable regions that are more vulnerable to acidification as we understand it. First of all, we all kind of knew that the high latitude regions, even though we don't sample them very well, as you can show here, are probably one of the most vulnerable regions. The reason for that is that in colder waters, more carbon dioxide is taken up more readily, and the concentration of CO2 is higher in those colder waters initially, and so that the saturation state is already low, and we will be taking it even lower. And so these areas, the very high latitudes, are already very susceptible. In fact, in the Arctic Ocean, we have regions in the Arctic Ocean that in the summertime are undersaturated. Similarly, a big surprise for all of us is that these upwelling zones, as we found here in our region in the California current system, bring up cold water from not really deep depths, from actually essentially just shallow depths, from anywhere from 150 to 300 meters. And these are naturally enriched in CO2. Then you have the overburden of anthropogenic CO2, which penetrates down to 500 meters. Therefore, you already have an additional source of CO2 on top of that natural source of CO2. And that increased CO2 from anthropogenic sources puts us over the top into corrosive conditions. That's what the Gruber et al. Paper said. In the pre-industrial world, we did not have corrosive conditions. Right now, we're just beginning to see it a few percent of the time. By 2030 or so, as much as 50% of our water on the Washington, Oregon, California coast will be in corrosive conditions. That is very, very disconcerting, is about what our future lies. And so these represent very vulnerable regions. Same thing will happen off of Africa and Portugal, and certainly is happening right now off of South America. Many of these places, we haven't even looked at them yet. We haven't seen that process yet. We know exists, but we just haven't looked for that process yet. There are other areas that are important because of the vulnerability of the species themselves, and many coral species are very, very sensitive to changes in CO2, and their sensitivity is again a direct function of that saturation state. And so even though the saturation state is high, usually about 3 or so, a change down to 2.8 can make a significant difference to them. So they are vulnerable areas just because of the uniqueness of those ecosystems. So in almost all the national and international plans, we've developed a strategy. It's a very strong observational and monitoring program that is tightly coupled with the biological studies, and so that we can see chemically and biologically what is occurring. So these ecosystem impacts are tightly coupled. We stressed that heavily when we began to write the Washington State Initiative on Ocean Acidification. I think this is one of these things we need to carry forward. We have to tightly couple those responses and understand them. The model changes and responses, we haven't really touched model changes in any kind of detailed manner yet. The few papers that we have shown that combined effects of acidification and other stressors, particularly temperature, perhaps other stressors as well, are significantly important. On our Washington, Oregon, California coast, the combined effects of stratification that is caused by global warming and CO2 increase will lower that pH by another 80% or more within the next 50 years, giving us a pH change as low as 0.5 pH change units because of these combined stressors. We need to be prepared for that. We need to have models that explain that more carefully. And in the coastal regions, you need higher resolution models that include the chemistry. Most of them do not. And we need to work on adaptation strategies. We have found that with the work that Alan Barton and colleagues have done in the hatcheries, is adaptation strategies is exactly what's keeping those organisms alive now. But the adaptation strategies that we have developed to keep them alive right now will not work in 50 years. So we have to work harder on developing those adaptation strategies. And what are we going to do in the field when those organisms get impacted? We got to develop adaptation strategies for them as well. We have a long, long way to go with this. This is just the example of what we have in the California current system as of 2011. I hope I will be able to update that very shortly. We are working through many regional associations and observing systems working together collectively to gather data and to work on data. Within the West Coast, we work primarily with the IU's Integrated Ocean Observing System, but as Gretchen pointed out, we also work through Mega's group. We're working with the local hatcheries, we're working with Aquaria, we're working everywhere we can to begin to coordinate data from a variety of different sources. The primary moorings that we have laid out right now are very important moorings. We are all associations, sometimes working directly with NOAA, but also working with the universities, Scripps and Oregon State and other groups working together. We want to expand this capability and expand the network as much as the resource will allow us, and continue to get a better understanding of the large-scale physical and chemical oceanography and how it relates to the hatcheries and how it relates to the local ecosystems. I argue that we need an early warning system. It means we combine the observations and the model, and the data sets have to be all integrated to make that work. So what we need then is to start from where we are now with CCAN and expand from CCAN and take what lessons we learned this morning and the lessons we will be talking about and begin to approach this from a worldwide approach and see if we can't have a worldwide observing system that builds on the lessons learned here with CCAN. This is why we play such a pivotal role, why we're going to have a lot of attention paid on us, because the successes we have here will be developed in the worldwide network. One of the things that we do have that I think is particularly strong is the IUS observing system in the United States. And this takes all the observing capabilities, brings them into a common data format, and allows the data to be displayed in many different approaches, both satellite data, observational data, moorings, floats, gliders. Whatever we ask to be brought in, they will take in, and we'll coordinate it out so it can be observed by everyone. You can see here that our observing capabilities are fairly strong now. We have exceptional mooring capabilities with observing systems for pH and PCO2 that are quite successful. The new work with the Durafect gives us really good certainty that we can make good measurements over long periods of time. In the SAMI pHs are now continuing to get better and better, so we can do both surface and subsurface measurements. We have made careful comparisons between the various techniques, and generally speaking, we need to calibrate each one individually. That's the problem with them. But once we do that calibration, they tend to maintain that calibration for a certain length of time. You do have to know when they go awry and be able to deal with that. That's why we have multiple parameters that we would like to look at. The IUS data system is very strong because it can map the data. It can do assessments of the data and filter data. It can provide overlays of data. It can look at these in terms of regional maps. Here is an example of what the IUS observational capabilities are at present, and you can see we're looking at moorings, floats, and gliders, near shore, estuarine observations, as well as far offshore. These kinds of data sets can be displayed in real time. Here's the UW NOAA sensors that we have on the moorings right now. We now have similar sensors that go on at Taylor and Whiskey Creek, and we even are now working to have them in local aquaria. This is the kind of integrations that we're asking for, where all the data sets can be displayed, uniform data display, and uniform accessibility in real time. We can also work with models and put models in the same context. And here's an example of such a model off the Columbia River. And you can take the same kind of output products from models and put them in that context to give you the kind of granularity you need to be able to make predictions and allow us to give ourselves opportunity for what I would call a early warning system. But these models are not there yet. They need more work. They need to integrate the carbon measurements and the biogeochemistry into the physical models. The physical models are really quite good at our high resolution, but integration still needs to occur. Now, if we look at the international world, we can see that there are many, many countries that are working very hard to have national programs, in some cases international programs. With the EPOCA program, which is the oldest of the programs, 10 countries have been involved, around 30 laboratories. The United States is commensurate, about 36 laboratories. United Kingdom has in the neighborhood of 26 laboratories. You can go through the list and you can see each country has invested their resources to address ocean acidification. The effort now is to bring those resources together in a collective group. And the way we have done this is by the SOLAS-IMBER Working Group on Ocean Acidification, which is an international effort which has now just recently evolved into the International Coordination Center. So this is the way forward. And this is a group that will begin the process of coordinating all the activities of the member nations and develop a coordination for communication and promotion of research and facilities, develop a capacity, develop the training of students to support the science and particularly international scientific experiments. And they've developed a number of different activities. Some of the best things that we've done so far, for example, is the early training activities, the development of best practices, which Andrew was one of the leads on, and we're now just getting into such things as data management and outreach. So we're just getting this started. It is an international effort. They've received funding now from several countries, and it's just, will be starting this fall. The observational network, again, is something that's more of a idea at this point in time. It was developed as part of this SOLAS-IMBER Ocean Acidification Working Group. We had our first international meeting that was led by Jan Newton and Steve Weisberg in June at the University of Washington. It was a very big success. We got a lot of good recommendations. We're hoping to get the report out very, very soon. But it does mean it's just a first step on what our vision is for an observing system. And as a result of that meeting, we developed our website in which you can actually identify which observing systems are available right now. And if you click on any one of these observing systems, it will give you the resource for that information, the PI involved, the name of the program, and how to get at the data sets. It does not have the data sets themselves yet because that data management has not been developed yet. The red dots are the plans for the future. This is the layout that this group of scientists, some 66 scientists, envisioned for the international effort for the future. And we also combined with it VOS cruises, voluntary observing ships, surface ocean ships, hydrographic cruises, floats, and gliders. So we are thinking very, very big, but we think the combination of all the individual efforts could give us the type of global coverage that we would have. You integrate this observing system for ocean acidification with the international carbon programs, and now you have an international carbon and acidification network, and that's the design of this observing system that we had in mind. We looked at what the needs and benefits of an international program would be. Scientifically, it means that we would be able to have uniform data sets in which we could calculate saturation states for the world oceans. We could provide the information that would be required for model input, and we, with the knowledge that wherever we're getting the data quality is the same, we would be able then to provide the kind of information all the biologists would need as input for their experiments. As I reported in February, this is critically important because we shouldn't be thinking in terms of CO2 levels at 700 or 800 parts per million as some of the surface models would suggest, because in the interior ocean it goes up to anywhere from 12 to 1600 parts per million. That's what the observations taught us that we didn't know from the models. And so we need to link up the experimental conditions with the actual observations in the field. For the industry wants to have, as Alan pointed out, real-time data right away, and in all the various hatcheries and hopefully at some point in time at the shellfish farms in order for them to make the kinds of decisions that they need to make with easy access to data and the very clear indices of what the data means. We as scientists have to work on these indices, get a better understanding of what they mean in terms of responses of the organisms. And government-wide, we have to begin to think about what this means for national policy. This could mean policy at the local and state levels in terms of how it deals with local emissions of CO2 and knots and SOx and nutrients and other species that do have an impact on acidification, how they can make sure that at the local level they're getting the kind of spatial and temporal resolution that answers the questions that the states needs, and how we would then develop appropriate adaptation and mitigation strategies. Right now, I think it's fair to say we have to start with this at the regional level, at the local level, because we're going to have more success at the regional and local level, and then move our way up to the national level. Another important component of this is education and outreach, and how important it is to reach out to the public and have them have a clear understanding of what ocean acidification means for them personally, how it affects their food resources, how it affects their livelihoods. And quite frankly, this is where we need a lot of work. Perhaps only 20 to 25% of our population know anything about acidification. So we need to make it personal, and we need to make it clear that it affects their lives. Now, in the international community, there is what we call a framework. And a framework is an overarching group that brings together all the different observing systems under one roof and helps to support those observing systems at the highest levels of our international government. And for us, this is called the Global Ocean Observing System, or GOOS. And what it does is it builds on the existing observing systems and primes a framework for developing collaboration between these individual observing systems and support at those international levels. This is a classic example of how GOOS works. It develops a coordination between all the major different kinds of observing systems, ocean sites here, satellite, Argo data, IUS, so we're represented here in IUS. They have actually reached out to us and would like our continued support with them. And when you look at the observational network that is represented here by the GOOS observational network, you can see it is indeed quite extensive. And this is the opportunity that we have to join the GOOS community and provide ocean acidification observations within the scope of the GOOS community so that we can truly be global in scope. We have to do this through observations themselves and through algorithm developments that allow us to use the resources of temperature, salinity, and oxygen to make approximations that will be useful. Now, as I said, GOOS has reached out to the ocean acidification community in a very aggressive manner because they now realize that GOOS is great for physical measurements. Now they have to expand themselves for ocean carbon and biogeochemistry, and so they are reaching out to us to come and join them in this effort. And they see that ocean acidification is one of those major issues we need to address. We can do this within their framework by working together with them, developing best practices and development of sustained observations. And there are a number of different entities within their international community, such as IOCCP and GOOS, and their panels that would work with our international groups like the ICCC directly to provide this degree of coordination. So where we started here with CCAN has made a very significant impact on the global community, and where we go from here is largely up to us. Thank you.
Do we have some questions for Dick? Dick, perhaps you could just give us a few words on exactly how you see observations within CCAN fitting into the kind of framework you've been talking about here.
So the way I view this as going is that CCAN has taken the lead on the West Coast by beginning the process of integrating observations in the coastal ocean primarily, and in the inner shelf regions and the coastal regions. We're now moving into the estuaries. That's the first initial step. And what we need to do is to develop all the data management that is required for that. IUS is part of that process, and IUS is willing to work with us to integrate and display those data sets. But we have to work at the next higher level, which is the National Ocean Data Center. And they're willing to work with us and directly with IUS to ensure that all the data are archived and integrated with the international data sets. One of their requirements is that they have to be a repository not only for national data but for international data, and they're willing to work at the international level. So we feed in directly from CCAN through the IUS program into the national archives, and from there to the international archives.
So Dick, the IUSians have done a great job of putting together the different COOS websites and observation compilation that we can all look at. Do you see this National Ocean Data Center or this GOOS, who do you see as being the entity that will try and integrate this on an international level?
The International Coordinating Center will have to make those decisions as they deliberate that. So that decision has not been made yet. However, the NLDC is welcome to work with them and have indicated they would do so. So I think we have a mechanism in place that could work, but it has to be ratified by the International Coordination Center.
Dick, I wondered if you could expand a little bit on potential mitigation and adaptation strategies. You touched on that briefly, especially when we think outside the window of hatchery settings and in natural, the natural climate, our natural environment where we have so many key shellfish species that are residing and living and going to be impacted by this.
Well, this is an area that I'm very sensitive to, because I think that the way we're set up in the United States, we do not have a particular agency that has a responsibility to develop the scientific basis for these adaptation and mitigation strategies. And consequently, we have to encourage them every way we possibly can to take this on as some new responsibilities. And the way we do that is the way we have moved this same way we moved it so far. The industry has demanded that the federal agencies respond to this, and the federal agencies will always respond to the industry needs. And I think this is the lesson learned as we learn every step of the way what the interactions are between the physics and the chemistry and the biology. We use that to develop experiments of adaptation strategies. And many of these experiments don't cost a lot of money. You can run an adaptation experiment fairly cheaply. I think the experiments themselves should be localized in areas where we're taking a lot of good, high-quality physical, chemical, and biological measurements so we can take advantage of that. But you can envision a lot of local experiments that could be run to see, for example, as an example, if certain types of eelgrasses take up carbon and therefore provide a location where oysters might do better. Those are experiments that can be run, that can be studied, and see if this is an application that might work. And here in Puget Sound, where we live, we have many, many eelgrass beds and many, many shellfish beds. The question is, can they live together or not? We just simply don't know yet. These are the kinds of experiments that have not been done. There have been a few experiments that are promising, but we could take them at the next level and see if these are commercially viable ways to go forward. Similar experiments like that, I think, are critical.
I guess I can't really help but comment on that. I mean, just from, we do a few native species in our hatchery every once in a while, you know, and if all this is true, if this is happening in the next 30 years, we've had some discussion about protected areas, I guess, for native species. Well, you better have a hatchery for your protected area. If the saturation stayed all year round for 1.5, you're not going to have a native oyster project. They're not going to live. It's not going to happen. So if we are headed this way, which I think everybody in this room agrees that we are, it's a lot harder than that. And, you know, we have a case study in eelgrass mitigation and Newgrass Bay. You know, we have tons of eelgrass in our very, very shallow bay. Newgrass Bay, where we get a lot of, we have water treatment systems in our facility. We turn them off when it's a bright sunny day and use naturally modified water. It's great. But as I've said to a few people before, the only problem is we can't stop the sun from going down every day, right? So that amount of photosynthetic activity also adds a very large amount of respiration at nighttime. So a lot of these mitigation strategies definitely need to be worked on. I'm very interested in working with macroalgae and bluegrass and things like that. But if we're going this way, they will not work. They will not work.
But, you shall probably always kind of start with a naive view. And I like starting with a naive view because then I can say things that are really stupid and you guys can prove me wrong. But there's probably a good reason why the Lumley hatchery has been successful, that we haven't figured that out why yet. And that might be an adaptation strategy we will utilize in the future, because we learned something from that hatchery that's unique to that environment that we can apply to the environment. And I think part of this is understanding the phenomenon well enough that we can take advantage of the solutions that come out of the science.
Just a follow-up, Dick, I was really impressed by your global view and your global maps. One comment here is the Pacific oyster is a global species. And, we're currently in the eye of the storm here in the West Coast, but other countries are having similar problems growing this species. The French, for example, have been impacted by a new variant of herpes that has not been seen before, that is decimating their production. This virus has now occurred in Australia and New Zealand. And so I think one of the things which might be of interest is to try and collectively gather together some of the information on the impacts of changing climate on this species as a biological parallel, if you like, to the many chemical and physical sensors that we have deployed throughout the world.
I'm really glad you brought that up, because one of the things that just happened in the last several days is I got contacted recently by a very high-level person in Washington state government, and threw out the idea that perhaps we ought to be thinking about assessments and what role assessments might play in this process. And of course, he was thinking in terms of assessments for Washington state. But as you bring up, perhaps an ocean acidification assessment at the international or national level might be something we need to be starting to think about now. And I think that personally, going through the IPCC process and understanding how that evolves from one assessment to the other, there's an enormous amount of information you get out of an assessment and an enormous amount of awareness of the problem that the international body of scientists and policymakers get out of these kinds of assessments. And I think we could be taking advantage of that now, because our science is now getting robust enough that we ought to be considering that. And I just throw that out as a way of addressing just what you suggested.
Dick, in your immediate response to my first comment, you emphasized the need for the data handling to make this an effective network. How do you see sensibly apportioning resources between the need to get the observations faster, cheaper, and easier, which is probably a matter for some investment, and the need to get the data handling going? How can we move this forward in a way that does give possibilities to more regional networks of being involved?
Well, I'm not sure I have a great crystal ball on that, but from my perspective, what I see very clearly is that the resources are inadequate for both right now. That's an honest assessment. If you visit the data handler groups, you can see there is overworked and underfunded as any of the observational groups. So what that tells me is that as an integrated national program, we have to address this, and we have to address it in a way that the states realize what's at risk to them, and therefore they lean on their senators and congressmen to impress upon them the need to move forward. The documents that have been written so far in terms of the strategic planning process, which is now available for ocean acidification at the U.S. level, is now available and for under review, do delineate what the true costs would be. And I can frankly say that the true costs that are delineated in these documents are nowhere near what we have available to us right now. So the pieces of information are there to really assess what the requirements are, and it's up to all of us to work collectively to move that along. This is a very difficult time in our federal government, but sometimes the needs are important enough to make a difference, and I hope they will in this case.
Thank you very much. So the goal of our discussion section here was really to ask, how do we get a view of CCAN that fits sensibly into the larger picture that Dick has presented for us? To get some sort of view as to how we can do this, given the constraints we're all individually and collectively aware of. How should we move this forward to have a regional observing capacity along the coast here that addresses the needs we see as appropriate to our region? One aspect that really came up at our meeting in Costa Mesa a year ago was recognizing that the simplistic, or perhaps I should say straightforward, view of an observing system of reliable sensors operating at all times in many places was unlikely to be available to us in the short term. Rather, we were going to ask, how could we take advantage of the fact that there were people with interests making measurements, often on discrete samples, sometimes with sensors that were perhaps at present inadequately calibrated, and how we could work to bring this together as a regional grouping of observations that could ultimately comprise a network. So as we move forward in our discussions, really we want to ask, okay, what is it that's really important to us? And one thing I'd like us to discuss a little at this point, and just to make sure we're fully comfortable with, is what are we really trying to measure? At the moment, it seems very clear that it's the changes in the CO2 composition of the seawater. And those of you who have had the time to spend on studying CO2 chemistry know that there are many ways to skin that particular animal. There are multiple ways to make measurements, some of them better than others, provided you really understand what you mean by better. Is it because it's cheaper? Or because the precision is improved? Or that it's easy to do? There's a whole variety of possibilities. And I think as we start to think about a CCAN network, we need to explicitly grasp this and recognize that ultimately it's going to be a mix of all of the above. Because people are going to make those measurements that they feel they should make, or that they feel they can make, ideally both, and we're going to have to live with it. So how do people think we should just broadly thinking about a regional network and putting it in place in the context of the much larger vision that Dick expressed? So this is going back down into the weeds from the multiple thousand feet.
Andrew, I guess I'm looking at it probably from your first term, from a more simplistic viewpoint, but I'm more interested, and I think we can kind of sell the concept of collaboration if we're not just looking at a change in CO2, but if we're looking at the likelihood of an impact on a particular group or industry or species. And if we look at these, what the impacts may be, then that may change who's involved in assessing or looking at the CO2 changes and starting to look at some of the other things that Gretchen brought up. You know, what are these biological interactions that are taking place near shore, offshore? And it's these impacts, it's the immediate and long-term economic impacts that were the driver to get this thing started, and I think they are going to be the long-term drivers of the ultimate goals of this group. And so priorities are going to be different based upon the different industries, you know, impacted by this. But I think maybe backing up or putting out the idea that Dick brought up, an assessment of what industries, what species, what groups of people are going to be impacted by CO2 change, or the impact of the increase in CO2 might be the big picture that I'd be interested in.
I wanted to offer a couple of perspectives that came out of that global workshop that we had in Seattle with the international community. And there were two concepts forwarded there, and both of the people who are responsible for those are in the audience. Burke Hales and Emilio Mayorga will touch on this a little bit more this afternoon. But I think to answer Andrew's question, recognizing that there's going to be a variety of approaches and a variety of needs, one of the things that this global community said is the most important thing to come out of this global network is the saturation omega of aragonite. If we can constrain the carbon system in order to get that, we're doing what folks need. So I offer that to you all for your consideration. The second good idea that came out of there were many good ideas, but pertinent to this conversation is the concept between weather and climate. Okay, so the type of precision that you need for weather level data, if it's 77.1 or 77.3 today, probably doesn't make a difference to me. I'm gonna go to or 87 or whatever it is out there. I'm from Seattle. 77 is a big number. Probably doesn't matter in the weather sense, but in the climate sense, that decimal place and probably one more is critical. So if we can constrain our data to talk about whether it's weather quality or climate quality and what those associated requirements are, that helps our system go towards what Andrew is saying, is that it'll probably be a mix. So I just wanted to offer those two viewpoints.
So in answer, in part, I think, to your question of what is it that, that you'd like to be measuring, I think the Clean Water Act has to come into play at some level. I think it's an absolutely fair question to say, Do we want to engage in the Clean Water Act process and the 303D process, et cetera, and is that the appropriate way of addressing this particular issue? But pH is a pollutant under the Clean Water Act, and at the moment, it seems to me, it's not totally clear to me that our water quality criterion for pH is a testable hypothesis given the data in hand. So that's going to vary. That criterion is going to vary state to state. In California, it's you have to be outside of the window of plus or minus 0.2 pH units outside of the historical range. And so at a minimum, I would think when talking about what an adequate monitoring system might be, would be one that would allow that hypothesis to be tested. So you've got to know pH with an accuracy and precision that allows you to confidently say where you are. Are you outside of that window of plus or minus 0.2? And you've got to know what the historical range is. And so that's going to require either data mining for historical data, or it's going to require good modeling so that you have an understanding of where you are in that window. So some states allow modeling, and some states do not. And so that's also going to vary within this country. But at a minimum, I would think that whatever you're measuring has got to be able to test that hypothesis of whether you've triggered that water quality criterion or not.
So there we heard two separate issues, one pH, one aragonite saturation state, and the context for it, which is what is the effect on organisms? Do we know that? Can we explain it clearly so as to awaken the interest necessary to ensure that this gets addressed adequately as we see it? Sadly, probably all of these have to happen at the same time and move it forward to get the progress we're going to make. Bruce?
Right behind you, right behind you.
I was just thinking about what Dick said earlier about it's really multiple things going on. It's upwelling, it's biological productivity, and respiration. So there's multiple things that only on some places along the coast do those things combine that in a way that we're seeing, trouble where we're actually getting the biological effects. And the fact that it happened in Washington and that oysters were affected is the reason that government got involved. So ultimately, I agree with Ian. It's the biological effects that are going to drive political action. So we don't really have a network yet, but we have a heck of a lot more buoys than we used to have. But still, I think ultimately we're going to find that those places around, say, the Columbia River or places like outside the front of San Francisco Bay ultimately are going to be the places where we see the biological effects. And it's not only true in North America, that's also going to be true in other places in the world, that these effects aren't really going to be everywhere all at once. They're going to be focused. And I think it's our job to learn, one, to be able to constrain better why we see what we're seeing. We kind of have a clue already, I think, but once we can constrain it, then we can start saying, well, these places are where we're going to see biological effects, and this is where we need to put our effort. So because I think the biological effects are going to drive political action, that I think we need to make sure that we're doing more than just saying, well, this is a good model of how the whole ocean will work. We really have to focus in on where those places that we're going to see damage.
So I'm going to follow up to Bruce and echo the same thing, because as a physiologist and just someone who works in the field and in the lab, I don't really ever think about the Clean Water Act and whether or not pH is going to bump over a number that probably has no traction in many places. So when we do our work, we ask ourselves over the last couple of years, where are the places where change is going to happen that will have a biological consequence. And for us at the time, we were largely thinking important marine ecosystems, particularly those that are coastal. So we have grad students working in coral reef systems in Moorea, and we're doing a lot of work on the California, Oregon coast. And, you know, as my group, so I'll speak personally, has worked on this for 4 or 5 years now, we've, you know, come a long way in understanding the environment. And there are parts of me internally that think that we're pushing on a threshold now, that some of the things that you all are seeing in Oregon and Washington at the hatcheries with the growers, and the things that we see in our wild fisheries in the Santa Barbara Channel, that we're moving into this zone where, in fact, the intensity of the effect's going to be local and focal, is what I always try to say to myself. And part of my thought process has been to go out and look for those things. So we also work in the Antarctic because we think that's a place where the biology might face these undersaturation conditions first. And I didn't attend Jan's meeting, but I would agree as a biologist, we really love to know saturation state. If we had to offer up one number, pH is awesome, and it helps us do things in the laboratory, but understanding the saturation state is really where the rubber hits the road, and it helps everybody from a global perspective.
To follow up on that, an idea that we're playing around with now in the Blue Ribbon panel, and probably will make a recommendation on, is that the Clean Water Act can become an instrument for the development of better observation systems to look in these places, and might be one of the ways in which we get a better handle on this and learn more about how to do the data gathering it takes to be able to adapt to the extent that we can. And I think Alan's point is a fair one. We don't know how much we can, and there may well be really important constraints. But for the Clean Water Act to function as intended, it's going to need a finer point that's more biologically focused. It's going to need to be able to be both technically and legally sound water quality standards. To do that, you have to start in a place or a few places where you actually know something about both the chemistry and the biology, and look there to start to figure out, can you define a water quality standard there, which is testable and which has consequence in the real world, not a legal abstraction of 0.2 of a point pH, and that you could, if you had to, defend, and both on technical and legal grounds. That is a pilot project that we think is a logical outcome going forward, and it may well be the kind of thing that would be useful for CCAN to be involved in.
Andrew, just one quick thing. I got distracted and forgot to say that what Bruce is arguing for is that CCAN has the opportunity in an environment where we don't have unlimited resources and time to identify those critical places for Brad's experiment.
I was just going to add that I'm personally kind of hesitant to narrow down our list of most important parameters to only carbonate saturation and pH, because I don't think it captures some of the organismal responses that people have documented that don't have to do with shell chemistry. So there are other physiological ramifications of increased CO2 that are not just specifically about shells. Now, Burke is going to argue with me.
I think, I'm not sure what Burke would have said, but the point that I would make is that perhaps the key that we established at the meeting in Costa Mesa was to say we needed to understand the CO2 system sufficiently well to be able to state what the aragonite saturation state was, in which case the kind of information you're talking about ought to be inherent in that. And if it were not, that's clearly a fault.
So I'll just go ahead and tell you what I was going to say, and that's it. If you know omega, since we can't measure it, that means that we had to have measured two. Why am I so much? If you know omega, you know all these other things that you want to know about the carbonate system. That's why we put it that way, is because you can quantify it with an accuracy and a precision that makes sense. If you can make the measurements to constrain that well enough that you can put those kinds of accuracy and uncertainty estimates on it, then you know pH as well or better than if you had measured it yourself. The second thing that I want to say is that what Tessa brought up next is a hugely important point that we grappled with seemingly endlessly in Seattle. And that's that there's a basic level of information that you need to have to study ocean acidification. And because I'm a chemist, I think that is the carbonate chemistry. And I would argue that you could make every biological measurement on Earth and you still would know nothing about the ocean acidification response if you didn't constrain the carbonate chemistry. And so I felt, and I'm not sure exactly how this came out in the final report, but I felt that there was this sort of baseline set of measurements. We got in trouble because we called it tier 1 and then everybody got their feelings hurt, and right? But the next step is if there's a baseline for the measurements that you want to make, and then there are a set of responses that you want to make in the context of that baseline, we need to hear about that, because when we tried to get that next set of measurements at that meeting, it went everywhere. Vanadium, oxygen isotopes. I mean, just nobody could come to a consensus on what needed to be measured in terms of response.
So I'd like to third my comments about the fact that it's more than just a aragonite saturation state that would be important for understanding biological responses. But one thing I was wondering about from a robustness of calculation standpoint, if we had a map of aragonite saturation state, let's say within the CCAN network, and people were making those measurements based on pH or DIC or whatever it was that suited their fancy, would that map be more or less robust given the nature of making the calculation of omega? This is not a question that you guys could answer this, but I don't know.
Just a quick statement on that. First, the quality of your assessment of aragonite saturation state will depend upon the quality of your CO2 measurements. That probably varies from place to place, from person to person, from lab to lab, from day to day. So the goal I think we should probably try to come up with is what's a level that would be adequate for most of what we want. Because going to get the best possible, it will certainly not provide you a map. It'll be a few individual locations that you have it. And we probably should come back to that discussion further this afternoon.
One other aspect that I think we may have been missing out on in this discussion, we've broadened our discussion as an industry. We've broadened our discussion since we've gone forward with this. As Alan will tell you, when they first started having problems, we all thought this was a Vibrio tubeaceae issue, and then realized it was related to pH, and now we're looking at saturation states. As time's gone on, I've become acquainted with a woman that works as a microbiologist with NOAA in Seattle named Linda Rhodes. And I think we're missing out on the microbiological factor in this, and the role it plays in the biochemical changes at the ocean-water interface. And I think it's an important factor. We've got the chemists, we've got the biologists. I think we need to bring in the microbiologists. I think we're missing part of our key here. And I would like to invite all of you that if you know people that are prominent in that position, to please talk to them and see what they think.
So to recap what I'm hearing at this moment, we're saying, okay, it probably makes sense to make CO2 measurements that would allow us to look at the saturation state, that would allow us to understand how the pH is varying, that would allow us to provide the context for the biological organisms that are being made. Sorry, the biological studies of organisms that are being made. The piece that's still a little alien in my mind, and I'd like to have people comment on this because it's come up in a variety of ways, is this concept that there are indeed fragile areas. It's often asserted in ocean acidification that these hotspot areas exist. And certainly, one can define them chemically and say, this is the place where you are most likely to have low
saturation states, where low can be defined in any way you choose, but once you've defined it, you can define where the places would be. What's much less obvious to me as a chemist listening in and looking at the literature is that this is inherently a biological hotspot. Clearly, these are chemical hotspots. To what extent should that matter to us? What do we need to think about to say that that is or is not so? A number of people have used this, and I just welcome people's input onto this problem, because in discussions I've had with a number of my colleagues over the last few weeks, clearly there is a significant number of scientists who are going, what do they mean, hotspots? Yes, the CO2 chemistry would change in the way they're saying. What does that mean for the organisms? Really, we don't yet know. Deathly hush. I think that is, as I see it, one of the real goals for this is to make sure that the CO2 context and the biological studies must go hand in hand. Because my own opinion on this is that one of the easiest and most correct answers when asked about ocean acidification is, we don't yet know. And that's perhaps not as helpful an answer as we would like to give. It smacks certainly of the classic academic need more money for research without being very clear as to quite how we would do this. So I think as we go forward and ask ourselves what it is that CCAN should be looking to put together and to incite as a pattern of dealing with this moving forward, this synthesis between the measurements and the biological studies is clearly important to all of us, as we have seen now at a number of meetings, of which the two clear examples are one, the CCAN meeting in Palo Alto, where it was very clear that some amazing biological measurements could be made, and nobody was convinced that we were yet in a situation where they should be made really generally. They were very focused in many cases, and Gretchen alluded to that earlier. And the comment that Burke took home, and I share his take-home message from the meeting in Seattle, which is that everybody agreed it was probably a good idea to know the simple physical and chemical measurements, but when you went beyond that, the degree of unanimity dropped very sharply as to what the next measurement ought to be. And it was, I think, in part, the answer was, we don't yet know. Pauline?
Well, in regards to the question of what are the biologically relevant locations, I feel like since there is such a long legacy of ecological coastal research along the California current ecosystem, we already have certain areas that have been designated, things like national marine sanctuaries, LTERs, places where there are already long-term time series in place. So we have already established to some extent what areas where we understand the biodiversity, where we understand whether certain areas and estuaries have unique fauna, and areas where we have a large amount of data about the biodiversity and even sort of the change in some of that biodiversity over time. So I think in some regards, we already have certain areas that we think, at least along the California current ecosystem, are biologically interesting and important and contain species that are both of commercial interest but also of biodiversity interest.
I think that's right. I mean, I think we have already a set of places where we know a lot, and we should keep studying those places. But I think that, if I recall, and as Gretchen already mentioned, we talked a lot about what we could measure at biologically at sites that we were making chemical measurements through these observing efforts. And we talked a lot at the Palo Alto meeting about things that would be really informative, that maybe were impractical to do on a really broad scale, or with really high temporal resolution, and sort of came upon measuring recruitment and settlement as something that was inexpensive, that integrated a large number of aspects of biological response and was possible to do across this whole network. And I think the idea was to use that to define where the hotspots were, because we didn't yet know exactly whether they would be in places that we already had a lot of information, whether the hotspots were exactly where the Whiskey Creek hatchery is, or whether the hotspots were somewhere else that we didn't understand because of the complex nature of all of the different types of physical and chemical factors coming together to affect biology. So, I think that we talked a lot about this, and we should go back to those sorts of discussions because they were really useful.
So maybe this is probably where Gretchen's headed as well, as a Somero student. But over my career, there's been DDT, and there's been the ozone hole. There's been lots of things. Some of those things never, like DDT, never happened before. Things like ozone are part of our environment, but maybe increasing. I'm not talking about UV irradiance, but we learned a lot after the fact. It was all clear by going to places where that was more common, like high altitude. And I think part of the pH story is new, and part of it's just we're making measurements and thinking about things that, like upwelling. There's always been upwelling from low oxygen water that's probably been corrosive. We just never put pH meters along with our oxygen meters. So, I think there's a lot of, the Rio Negro's pH 5. So, I think there's some places we can go, even along the California coast, where upwelling's been intensive relative to areas where it's not been intensive, and maybe learn something just by opening our eyes a bit.
Yeah, so returning to Andrew's question and your question about hotspots, to me, in a biological sense, I'm not convinced that there's any reason that biological hotspots should coincide in time and space with chemical hotspots. I think that we have to, when we think about biology, we have to consider the history of exposure and the evolutionary history of exposure. And in fact, those real, what we think of as chemical hotspots, the organisms may not care too much. And they may not care as much as organisms that have never seen these conditions before. So I think trying to couple the two without evidence, strong evidence of coupling, is perhaps not the best way to proceed. I think when we think about biology, we want to think about one way to think about it is thresholds of adaptation.
So one last oh, sorry, John.
Just to, and I know that we keep going back to the hatcheries, but Alan and I talk all the time about how we have essentially a research facility that's running, and that really, we now have chemistry data in these hatcheries, and this is just, I think, one part of what should be in this network. But with a little bit of work, and we have a plan that we put together for the USDA, which unfortunately was not reviewed by people who should have been reviewing it. But with a little bit of work, we can coordinate those biological measurements of larval success in these hatcheries. And I think Brad may have said this first, was that every tank change is a bioassay in those hatcheries. And these guys are looking at that, and there's some record keeping, but we're not really coordinated in how they're doing that. And I think, working together with them to coordinate those measurements would give us something that's really tangible. It's a very small subsection of this California current ecosystem, obviously, but it's something that we can grasp and do pretty easily with even just a microscope, looking at some size and survival data without a whole lot of extra effort, in my opinion. It's more effort on their behalf, and we would need someone to help make those measurements. But
so to follow up on all this a little bit, so the Omegas group that I'm a part of is really focusing right in on this, the biophysical coupling of what we see in the water and what part of that signal is biologically relevant. And recruitment, organismal performance, gene expression is included in that perspective. And in a lot of ways, we're just doing the biophysical coupling, but the thing to really bridge to from a very broad perspective is that as we all do this, so George, your activities and any movement to do this, one can take this so far as to ask, what are we really looking for? And furthermore, how can it contribute at a very large management scale, so maybe marine reserve design. So when one goes out looking for quote-unquote hotspots, from a biology standpoint, if we find a place that has a lot of environmental heterogeneity and what we would maybe, let's call it a big OA signal, a big acidification signal, one might want to study and preserve that area and not say, God, these organisms are going to get smoked. But we're learning from our laboratory experiments that those are the places where there's grist for evolution. It's those populations that are the ones that we want to ask, is there enough variance, genetic variation in that group to evolve? So then there are also places that we would find that don't have a big signal, that are really gentle and sweet, and there's not a lot of random heterogeneity in seawater chemistry. And those could be stocks that are very different. And so when we actually reserve areas like this, Alan's comment reminded me of that, we should have all these different fishing and aquaculture perspectives involved when we make reserve designs. And when we do the activity, CCAN can be the one that suggests, hey, looking for hotspots has deep consequence depending upon how you look at it. What are you preserving? I mean, what are you conserving?
So I just wanted to follow up on George's comment, and you know, this was a completely fortuitous thing that was entirely driven by Alan that got us working with the hatchery. But what I wanted to point out is the economics of working with these operations, who are production facilities, as research facilities. You know, I think there's symbiosis in the measurements that we're doing that are helping the hatcheries out. That, you know, and we get some return on that is beneficial to us. But I also want to remind you guys, I mean, the cost of having the hatchery produce a batch of spawn relative to the cost of you bringing in graduate students to train up, to culture these organisms, to build culture facilities yourself, is minuscule. I mean, Alan, what is it, if I were to buy a farm-sized vial of larvae, what does it cost? $150 a million, right? I mean, that's outrageously cheap, right? And if we just buy them, you know, I mean, the thing that happens now is that they're a production facility and we're a research operation, and so we can't say, grow a bunch that you know are going to die, because that's not how they operate. But if we buy them, why not? I mean, I think a huge part of what we can do would benefit the hatcheries and take advantage of their strengths without us having to reinvent the wheel.
Okay, thank you, everybody. The lunch you hear in the background there, I'm sure these continuing discussions will continue both over lunch and into the afternoon. Thank you.